Hello there, this is a geometry video. It is chapter 10, section 5, and today we will be discussing tangents. So to get started, we've got some vocabulary for you. A tangent is a line in the same plane as a circle that intersects the circle in exactly one point. So basically, unlike a chord that we've done in the past where a chord will go through the circle and it'll enter the circle in 2 points, it'll intersect here and here, for example. A tangent line only touches or intersects the circle once. So I know that you think of intersect as going through it, but really what you want to think about with the tangent is basically that it touches it at that one point. And this is kind of where the tangent is happening here. You can see the tangent happening here, and here's the point of tangency. But let's continue. It intersects the circle at exactly one point, and we call that the point of tangency. Line AB, which is over here in this diagram, the red tangent line there, is tangent to circle C at point A. So point A would be what we would call the point of tangency. Segments AB and ray AB are also called tangents. So the tangent doesn't have to be a line, it could be a segment or a ray. A common tangent is a line, ray, or segment that is tangent to two circles in the same plane. So for example, in this case, we now have this line L being tangent to circle G, but it's also tangent to circle F over here. So it's tangent to two different circles. Same thing's happening here with these two circles. Line L is tangent to both circle G and circle F. In each figure below, line L is a common tangent of circles F and G. So we're going to go to our first example here. And we are being asked to copy each figure and draw the common tangents. If no common tangent exists, then you can state no common tangent. So obviously in my case, I have it kind of easy because I don't have to copy the figure. I can just do it on here on the board. You will have to copy the figure onto your paper just do the best you can. You don't need to have a compass, but just try to make the circles as similar to what you see in the example. So here we can actually see that you have a tangent line to the, there's actually two tangents. So I'm going to go ahead and draw those for you. In this first example, we have tangent that's going to kind of go this direction. So I'm just going to take my straight edge and try to get it to where it's touching both, like so. And then of course you have the same situation happening on the other side, which would be something like this. So there are my two tangents. Now obviously I kind of missed the mark there a little bit, but you kind of get the point. Those are my two tangents. But for part B, for these two circles, because they're not intersecting, we actually end up with four tangents. We have a very similar thing going on where you have a tangent that is kind of this direction. And then you have that on the other side. See if I can get this a little better this time. But then you have a tangent kind of like we saw in the previous slide where it's going in between the two circles. So you've got a tangent going this direction. If I can draw this right. Did it mark it? I'm not sure my pen is actually drawing anything. And then you have one going this direction. So you have actually four tangents in part B. So there you go. Now you can try do it yourself number one, and then we will go on to our first theorem of this section. And here we go. We're going to want to get our guy out of the way here a little bit so you can actually see the bottom there. But here we go. Theorem 10.10. It says, in a plane, a line is tangent to a circle if and only if it is perpendicular to a radius drawn to the point of tangency. So whenever you see the if and only if, it means it can go both ways. That means that if this line is in fact tangent to the circle, then it has to be perpendicular to the radius ST. Also, it means that if the radius ST is perpendicular to the line L, then line L is a tangent. So it goes both ways. So in example 2, it says JL, which is right here, is a radius of circle J. Determine whether KL, which is this segment here, which appears to be tangent, determine whether KL is tangent to circle J, and then justify your answer. Well, since we know that this should be a right triangle, if in fact it's going to be a tangent, it would have to be perpendicular here. So this would have to be a 90-degree angle. And if that were a 90-degree angle, then the Pythagorean theorem would apply. But keep in mind that we know that this is the radius 8. So don't be fooled. This does not mean that the entire segment is 9. It means that from this point to K is 9. But we know that all radii are congruent. So this would be 8 here. So that means that we can actually take and get ourselves a Pythagorean theorem going on, and we can say that 8 squared, remember we have leg squared plus leg squared, so 8 squared plus 15 squared, if this is in fact going to be tangent, then this Pythagorean theorem should apply. And it should equal 8 plus 9 squared, because the hypotenuse would be 8 plus 9 together. So it turns out that 8 plus 9 is 17. So here we've got 64 plus 225, and then 17 squared. And it just so happens that 64 and 225 is 289. And lo and behold, these are all question marks at this point because we're not sure what's going to happen. But actually 17 squared is also 289. So there you go. Because triangle JKL is a right triangle, so since triangle JKL is a right triangle, then we know that KL is perpendicular to JL, which is the tangent line perpendicular to the radius. And therefore, which is what these 3 dots mean, therefore, then it's tangent. Therefore, KL is tangent to circle J. All right, so that's kind of how you do that. So you can go ahead and do it yourself, number 2, and then we will go on to our next example. All right, here we go. Example 3 says JH is tangent to circle G at point J. Find the value of x. But again, we're going to base this off of the idea that we know that triangle GJH should be a right triangle. So we can set up a Pythagorean theorem and then solve for our variable. So before you get too scared, let's just go ahead and show you how that's done. So my leg right now is GJ is going to be x squared. My other leg is JH, which is 12, so plus 12 squared should equal the hypotenuse squared. But the hypotenuse is the combination of x plus 8, so we need to put that in parentheses. And unlike in our previous example where we could take the 9 and the 8 and add to 17, in this case we can't do that, so we have to use some algebra. Hopefully your algebra isn't too rusty, but we're going to get x squared plus 144. And if you remember, when you have x plus 8 squared, this is not just x squared plus 64 squared. A lot of people think that's what it is, but it's not. When you have, and I'll just put the formula up here for you in case you don't remember it from Algebra 1, but when you have a plus b squared, quantity squared, the formula says it's a squared plus 2ab plus b squared. So it's not just a squared, b squared. There's this middle term that's either plus 2ab or minus 2ab, depending on whether or not this is a plus or a minus. In this case, a plus. So we're going to go at plus 2ab. And so don't forget that plus 2ab because that's going to be a huge deal. Another option, if you don't like the formula, is to actually FOIL it. Like do x plus 8 times x plus 8 and then go first, outer, inner, last. But honestly, the formula is the easiest way to go. So hopefully you can do that. That's what I'm going to be using. So I'm going to say a squared is going to be x squared plus 2ab means I'm going to take 2 times x, which is 2x, and then times b, which is 8. So 2x times 8 is 16x. And then lastly, plus b squared, which is 64. Alrighty? So don't forget to do that. And what's nice about this is that when you try to combine like terms, you're going to end up subtracting the x squareds, but they're going to cancel. because there's an x squared on both sides. So if you were panicking about you weren't sure how you were going to solve this, you don't have to worry about it anymore. Now what we're going to do is we only have this x variable here. So we're going to subtract the 64 to this side. And 144 minus 64 is actually 80. And on the other side we have 16x. And when we divide by 16 on both sides, we get that x actually equals 5. And that's what they wanted us to do, find the value of x. So x equals 5. So that is how that little cookie crumbles. So you can go ahead and do it yourself. Number 3, there's a part A and a part B. And we'll move on to constructions. However, I hate to have to disappoint you just a little bit, but I need you to write down these steps as accurately as you can. And you don't have to have the pictures exactly, but it wouldn't hurt to have them so you can see them. Like, we are going to have to do this. But I think that with the construction, it'll be a lot easier for me to go over this part in class. Besides that, I don't have an actual compass with me right now, so I couldn't do it for you on the board anyway. But I do need you to write these steps down so that we can go back to it later in class. All right, so we're going to go on to example 4. And in example 4, we have another theorem. And this theorem tells us that if two segments from the same exterior point, so here's the exterior point, it's outside of the circle, are tangent to the circle. So this point is tangent to the circle with the segment AB, but it's also tangent to the circle BC, that segment. So since both segments are tangent to the circle, then they are also congruent. So basically, AB and CB would be congruent segments because they're both tangent to the same circle from the same exterior point. So keeping that in mind, in example 4, we have a diagram, and it says that AB, you can see a very similar diagram. AB is tangent, and so is CB, and they're both extending from the same exterior point. So that means that according to the theorem, that both the segments are the same. So again, a really simple algebra problem. We take our AB, and it has to be equal to BC or CB, however you want to. They're technically the same thing, but let's just stay consistent here. AB has to equal CB because they have the same exterior point that they're tangent to. And so AB says it's x plus 15. And CB is marked as 2x minus 5. So we're just going to do some algebra here real quick. Subtract x from both sides, add 5 to both sides while we're at it. And it just so happens that 15 plus 5 is 20. And then over here, you've got your 5's that are going to cancel. Your x is going to cancel there. 2x minus x is actually x. And just like that, voila, you're done. X equals 20. And that's all you have to do there. So you can finish this example, or sorry, let's do a stop question. And then we're going to go to our last one. Example 5. And to do example 5, we kind of have to understand this idea of circumscribed polygons. And so basically a polygon is circumscribed about a circle if every side of the polygon is tangent to the circle. So here you have some examples of circumscribed polygons. So every side of this triangle, for example, is tangent to the circle. Here, this quadrilateral, every side of the quadrilateral is tangent to the circle at some point. Over here, you have examples of polygons that are not circumscribed because not every side is tangent to the circle. So that's kind of how you know the difference. So obviously, if it's going to be circumscribed, then one thing that you can know automatically is that if it says it's circumscribed, then all of the sides are tangent, whether it appears that way or not. So in example 5, it says a graphic designer is giving directions to create a larger version of the triangular logo that is shown. If triangle ABC is circumscribed, so they're telling us that it's circumscribed, which means that all of the sides of the triangle are tangent to the circle G. They want us to find the perimeter of circle ABC. So this might appear to be a bit of a doozy, but it's actually not that big of a deal because all of the information is already on the diagram. So we're going to show you what that means. So for us to find the perimeter, wouldn't it be that difficult? We just need to add up all the sides. But what's happening is you have all these missing pieces. We have AD, but we don't know AE. Well, it turns out that AE is the same as AD because they're both tangent to the same circle from the same exterior point, our theorem from earlier, which means that they would both be 8. In a similar fashion, we know that FB is the same as EB, right? So I'm going to go ahead and call it BF. So the distance from, we know that the entire length here is 10, but I need to know what each piece is separately because I want to be able to fill in this gap here. And so that's what I'm doing right now. So I know that BF is the same as BE for the same reason, which is that they're both tangent to the same circle through the same exterior point. So that would be 7. And if if BF is 7, then I know that CF, which is this little guy right here, CF, would be equal to the entire segment, which is CB, minus BF, which would be 10 minus 7, which is now 3. So I hope that you followed there. So CF, which is this little piece here, would equal the entire segment, which is 10, minus the distance from B to F, which we know is 7. So that means that CF is 3. And CD is the same as CF. And we just discovered that CF is 3. That means CD is 3. And now we have all of our missing pieces. And to find the perimeter, we're just going to say that perimeter is equal to 8 plus 8, which is 16, plus 7 plus 10, right? So this is 8, 7, this whole thing is 10 plus 3, and that's it. We've got all the pieces together there. So now we've got 10 plus 7 is 17, plus 3 more is 20, and 20 plus 16 is going to give us 36 total feet for the perimeter of that figure. Alrighty, so even though it seemed like it was going to be a big doozy, it actually ends up being pretty easy to figure out. So that is how you do example 5. So now we're going to have you do this do-it-yourself question. And once you have completed this do-it-yourself question, you will have completed your notes for this lesson. And I will see you in class. And thank you for watching.